So let's go ahead and see what we get. Same kind of thing. The red particles are active and they are falling down. They're hitting this collision environment group. The collision environment group is set to neutron, so they don't respond. And we can see them just kind of sit there. Let's go ahead and set the collision environment group. Let's make sure you got those selected, and we'll set them to active. And we'll see that now they respond and they get knocked around. Let's actually move our emitter sphere up there. Okay, let's come back to shape collision. Something we want to look at is called size as mass. If we check this, it's kind of like using the size operator has a switch for it too. Or maybe not when it's left out in the open here. Let's try it over here. Oh, I'm sorry, it's mass, not size. So when we connect mass, let's take a look at the mass operator. Mass has an option for size as mass as well, where it's actually going to go ahead and treat those as its actual mass value. The size as its mass. So if we did this, we'll duplicate that guy. So now we're saying, okay, I want the red particles, I want your size to be your mass. As well for the collisioning V, I want your mass to be the same as your size. So these cylinders are quite a bit larger than the cubes, so they get bounced around less. The cubes are going to be lighter, and so they're going to bounce more. Cylinders are going to be larger and heavier, so their size is going to have more mass. But let's go ahead and do this. Let's switch off the size as mass, and we're going to tell the red guys to weigh 5, and we'll tell the collision environment just to weigh 1. Not a huge change. Let's go ahead and try it a little bit more. Or maybe our size as mass was checked on shape collision. So let's do this. First let's just see where we're at. Yeah, look at that. So these red are really affecting the collision environment. So even if the red was set to 2, let's see what we get. Yeah, quite a bit of knocking around. But let's go ahead and if our reds are 2, let's set our cylinders to 20. And watch their mass now. One of them gets a little affected over there on the side, but for the most part they don't really respond. Their mass is going to prevent them. So this is a very accurate type of shape collision. Let's come back up. We want to take a look at something else. We'll set their mass to 1 and let's leave the red's mass at 2. Collision environment mass is 1. We want to take a look at the one last simulation type setting. We looked at active, so it responds and it's active in the simulation. Neutron basically acts like a deflector. And frozen will start the particle off frozen in the simulation so that he's not actually going to be affected until he's hit by something. And we have some controls to affect and determine when he's going to turn on, and those are under this frozen first activation area. There's a velocity threshold, so how much velocity has to be affecting him before he'll turn on, or how much rotation, as well as once he's hit, how much motion inheritance from that hit is he going to have once he's added into the simulation, once he's unfrozen. So let's go ahead and we've got our collision environment is set to frozen. Let's go ahead and see what happens. We can't really tell, it just kind of looks like they're active, but what's happening is they're starting off frozen, nothing's affecting them, and then these red guys actually are hitting them hard enough to go ahead and wake them up. Let's actually make it harder for the red guys to wake them up. Let's go ahead and set their rotation threshold to 360. Let's see if that does it. No. How about the velocity? Maybe the velocity have to be 100 or more. So there you can see, now these cylinders start off frozen, and nothing's hitting them hard enough, fast enough, or with enough rotation to actually wake them up. So they're just going to stay there frozen until something big, heavy, or fast hits them. So let's go ahead and we'll set these back to the defaults. Something else we have down here in this group, First, let's mention for each of the particle groups, you've got the ability, just like we did with the floor, you can adjust the voxel grid, which is going to change how the simulation engine analyzes the shape of the particle, and it's going to give him higher resolution and a more accurate simulation with a higher voxel grid. Just remember the cube with the divided box that's going to look at the particle shape and decide where am I going to calculate collisions for. Let's see. So that's our voxel grid. Then we also have edge samples. So like here on the red group, he's just a plain old cube. This simulation's pretty simple, so we don't see it a whole lot, but his edge here, he's only got one edge, and his edge sample is only set to 1. So it's only going to sample that edge only once. If we wanted to increase that resolution, you could just add more edge samples. And then we also have a velocity friction, which acts as a, let's see, it's going to define the relative speed difference between two particles and will cause a faster one to slow down when it hits a slow one. Definitely check the manual for that one. Let's take a look. We covered the frozen. Let's take a look at the deformation. Deformation's fun. It allows particles to, when they're involved in a shape collision, because see all these parameters here are shape collision. These ones are physics. This is a different shape collision dynamics operator we're going to look at in a little bit. But shape collision has an ability to deform the particles as they get hit. And we actually want to take a look at deforming these collision E and V particles. Let's go ahead and make them active. And let's do this. Let's set their, what we're going to do is set their maximum depth. Let's get an idea of what we're looking at in world scale. So let's go ahead and just create a little dummy sphere here. Okay, so with a radius of, say, 4, so diameter 8, that's pretty large. What the deformation is going to do for us is it's going to crush these particle shapes when they're hit. And so we can define in world units how much deformation is going to be possible, total, and also a radius, so kind of a fade out or an overall area. Yeah. From the point of collision, how far out are you going to calculate this deformation? Let's go ahead and set our maximum depth to, say, 5 and radius of 3. And let's go ahead and see what we get. Yeah, they really get crushed pretty fast. Let's do this also. Let's say maybe our maximum depth and radius of 1. So a little bit more controlled. We want to actually take a look at this third parameter, impulse threshold. This is going to allow us to limit when that deformation occurs. It's going to require an impulse value of whatever we set or higher in order to affect the deformation. Now the impulse threshold comes from the speed and the mass of the particle that's hitting him. So at 5 you can see we still get deformation. If we set the impulse threshold, maybe let's try 50. We don't see any deformation. So somewhere down in here, maybe 20 or so, you're going to find that there's going to be a sweet spot where whatever the speed and mass of your moving particles, once they hit those other guys, you're going to be able to dial in an impulse threshold that's going to say, okay, once it finally goes this fast and strong, then go ahead and deform. Okay, so that's deformation. Fantastic new addition to TP3.